says like 20 seconds or so, I guess it'd be good to
walk out there.
For the intro. Okay, if possible.
10 seconds.
But as we're going over.
Okay, so it's my pleasure to introduce today's speaker. Kevin Hoffman is a fifth-year grad student here at Purdue. He works in programming languages and systems, and in the past he's also done some work on aspect-oriented programming, and he's proposed an original, highly scalable dynamic analysis technique, which he's applied successfully to Java programs. And in that context, he's also interested in applying it to security. Kevin is a GAN Fellow and a recipient of the Halstead Award, and I'll let him speak about his ongoing research for himself.
Okay, thank you. So this work is about ribbons, and it's joint work between me and Harrison Metzger and my advisor, Patrick Eugster. This is work in progress. We submitted a paper, and anytime you have questions or something isn't clear, please stop me and ask the question. Make sure it's fully clear. So just talk, we'll give you some background, go through the concept, present our extension of Java language, which implements this concept, some of the system details implementing it, a micro benchmark we have from our system, and then current work and ongoing work. All right, so this is a security seminar, and I'm interested in practice, solving problems. So here we have from the MITRE Corporation a categorization. They looked at all the vulnerabilities, and they pulled out patterns, the top 25 most dangerous errors people make to introduce security failures. And if you look at these, a surprising number of the top 10 are due to data validation or formatting errors. And if you look at some of the possible countermeasures to the data validation formatting errors, the techniques, there's no sure solution. The techniques are all sort of spread throughout the code. They're difficult to implement. So for example, you have to track data flow. Is this variable that was received, could it eventually be used directly as part of the SQL string? And if so, have I properly formatted already or not? Or character encodings are really subtle. So if input's submitted with the wrong character encoding, it could miss, certain special characters that you're scanning for could be missed, and later when you transform the character encoding, those special characters could appear again. So it's pretty difficult to solve these, obviously, as they're a large part of the top 10. So systems typically have defense in depth. There's other mechanisms that are more general that try to mitigate what happens if they make one of these failures or errors. So one of the common principles is called least privilege. And the idea is just that you want to give the security subject the least amount of privileges necessary in order to do whatever task they need to do. Sort of damage control, if you say. Also, you want to make sure that your granularity is fine. So, if you have least privileges for your entire operating system, obviously that's not so useful. So if you have it at your process level, then the process is compromised. Anything the process could do, the attacker would be able to do. But if you can get even finer than that, it mitigates your scope of the attack. So the finer the better. The more often, from a security perspective, that you're switching, what set of privileges you have in a secure fashion, the more you can control, put security boundaries here. So some of the systems out there, in practice, operating systems, you've got discretionary and mandatory access controls inside of operating systems. ACLs, SU Linux provides a sort of type enforcement mandatory access control system on top of regular ACLs. However, these just deal with operating system resources, files and network sockets and these types of things. But what about the heap? what about all this sensitive, potentially sensitive data inside of a process? What is there to protect the heap? But okay, so keep this question in your mind, and next consider, does the heap even matter? So, if we look further in the top 25, here are errors from the top 25 that are related to heap corruption or heap manipulation. So about 1/4 of the top 25 is related to heap problems. You've got your classic buffer overflow, buffer overruns, improper validation of array indexes, various problems with buffers. And these cause serious problems. So here's another list from the SANS Institute that shows you the top 6 zero-day vulnerabilities for a 6-month period back in 2009, according to their classification. Yes.
So you're focusing on Java, so doesn't Java protect against buffer overflows? So in that case, it wouldn't be applicable?
Yes, so Java does protect against it, like you say, or any managed language. However, you still have a fair amount of code written in the native language implementing the Java virtual machine, or you have plugins that are native. And our technique, even though we've implemented our language extension in Java, you'll see later in the talk that it actually applies at the operating system level, the process level, and then at the JVM level and the language level. But true, all of these vulnerabilities here, the zero-day flaws, these are all native code plugins for browsers. So focusing specifically on this browser plugin problem, one solution, Internet Explorer, runs in a sort of lower privileges mode. It doesn't have access to most of the file system. But what if, if there's a flaw in one of these plugins, you still have the vulnerability of tabs or different domains accessing each other's data. So once the plugin is compromised and the heap of the process is compromised, that malicious script is free to go steal your credit card number from the banking tab you've got open at the same time, for example. So you can run plugins out of process, and Chrome does this, and Firefox is starting to do this. However, it makes the code much more complicated. It's a little bit less efficient, and it also makes things a lot more complicated when you want to have multiple plugins of the instances of the same plugin. But yet these plugins need to share some mutable state together. So what we're really after is this robust access control mechanism over the heap. So taking this example further here, say that we have Firefox open, we've got 2 tabs open. Each tab has some flash scripts inside of them. So on the left here, I've divided up the heap into different protection domains, as we call them, or just segments of the heap. Maybe your browser has some global private state that it uses for its own purposes. It's got some shared state, maybe the cookie data or the cookie cache or image cache or whatever it may be. You've got your document object model for each tab. You've got your specific flash scripts running in each tab, each with its own state, probably running on its own thread depending on how Flash is set up. And then you've got, any Flash-specific caching or shared state. All right, so, what does tab 1 need access to in order to perform its work? So you've got its own document module, any scripts running inside of it, and the global private and shared state. But not all of these regions are created equal. So here you've got, highlighted in red, a region that you may not want to have writable or perhaps even fully accessible by the thread running the tab, the first tab there. So how do we model these privileges and still have an efficient yet easy to implement and easy to write system? So there's some prior work on heap protection. Nooks is sort of a special purpose system for protecting device drivers inside the operating system, and it provides a sort of fixed structure for protection domains for device drivers and the different parts of the operating system.